Now we're going to finish up by looking at some extra operations that are supported for string keys when we use tries. Um, we're going to look at a couple of character-based operations that are quite useful and can be supported by the string symbol table API with tries. One important one is prefix match. So that's given a prefix like, say, sh, what we want is the method to return all the keys that start with that prefix. In this case, it would be shells, shore, and she. Another one is so-called wildcard match. So that's when we don't specify one of the characters or multiple of the characters. So we put a dot to say we'll take any key that matches the other characters, and we don't care what that one is. So .he would match she and thee. And another one is so-called longest prefix. So now we've got a long key, and we want to find the best match that's in our symbol table that matches that key. The key in the symbol table that has the longest match with our key. So in this case, the one that's the longest prefix of shell sort is shells. And later on, we're going to see applications of some of these. And the important idea for now is that these are easy to articulate, and not only that, they're easy to implement with tries and and ternary search tries. So we're going to take our standard API and add these four methods. Well, there's keys that returns all keys, and as is our usual practice, when we have a lot of things to return, we're going to return them as an iterable, so the clients can just iterate through what's returned. That's usually what clients want to do. And then we have keys with prefix, give a string s, and the iterable will return all the keys in the symbol table that have s as a prefix. Client wants to find the associated values, they can do gets to get the values. And then we have keys that match, so that's where we allow dot to be a wildcard in s, and we want to return all the keys that match s, taking dot to be a wildcard. And then longest prefix of s is the key in there, that's the longest prefix of s. We're going to see later on this particular one plays an important role in a more complicated algorithm. We could also go ahead and add all the ordered symbol table methods that we considered when we looked at binary search trees like floor and rank. We're not going to take time to do that right now. It's very straightforward. One thing that we haven't really talked about, but it's a good warm-up for the kinds of methods that we're going to look at for these implementations, is ordered iteration. And this is try traversal. So we're going to do an in-order traversal of the try. That is, visit the left, visit the middle, visit the right. In that traversal, we can maintain the sequence of characters on the path from the root to the current node just by adding a character when we go down and removing a character when we go up. And when we encounter values, then we can put out the characters that we have, and that's a way to pull out all the keys in the try. So for example, in this case, we go down and we have B, and then we hit the Y, so we can output, say onto a Q, we can output by. And then we go back and we have S, E, and A, and we find a value, so we can go ahead and put out the A. Now we drop the A and do the L, and SEL, and LL, and then we get to that S, we have a value, we can put out cells. And then we can drop these, get back to the S, and get to SH, SHE, find a value, and put the she on the Q. LLS, and put shells on the Q. drop all those values down to the H and get SHO, SHOR, SHORE, find a value and drop sure onto the Q. And then finally T, TH, and THE, and find a value and put D on the Q. So it's easy to, very easy to keep track of the sequence of characters on the path from the root to every node, and at every node check for a value and throw it on the queue. That's ordered iteration. And the implementations of these extra operations are just based on modifying ordered iteration. So this is an implementation of keys, which is essentially the operation that I was tracing on the last slide. So if the client wants keys, we make a queue, then we call a recursive routine that collects all the keys in the trie starting at that node, and given a null string, which is the sequence of characters on the path to the given node. When that recursive routine returns, then we just return the queue. And the recursive routine does encode what I said in words most of the time. This is for a trie. You could do the same thing for a ternary search tree with just a little more code. So for every character, we just move down the trie for that character, add the character to the prefix, and also pass the queue along. If we get a non-null value, we put what we have on the queue. When we get null, we return. So a very simple implementation of ordered iteration, recursive. So that's the implementation of the keys method. So prefix matches and other things like that are going to work just by modifying that. And you're familiar with prefix matches. When you type nowadays in your browser a search function, you're getting a prefix match of all the things that you typed or other people have typed that matches those strings. And you find that also nowadays when searching in your address books. It's a quite common function nowadays. So let's look at how that looks in an R-way trie. So what about finding all the keys in a symbol table that start with a given prefix? Well, we just search for that prefix and then just do a collect at the keys in that subtrie. So that's very straightforward. So you get the node that is the one you get to by starting with that prefix, and then you just call the recursive collect, and boom, you're done. Extremely simple implementation of keys with prefix in an R-way trie. What about longest prefix? And here's one that is very heavily used in the internet. If your query strings are IP addresses on the internet, and you have some given destination IP address, the router has a lot of IP addresses in a routing table, and it wants to choose the one that would get you as close to the destination as you can, so it's going to choose the longest prefix. So if you want to get to 128.112, you can think of these as hops on the way to where you want to get, where 11 is the final destination. And essentially this table says it knows how to get this far, and so that's what it wants, is the longest prefix. Longest prefix match of, say, this one, well, it doesn't know how to get any further than 112, and this other one only to 128. And this operation gets performed extremely often on the internet nowadays. Just a quick note, it's not the same as the floor function. It actually is a kind of a string operation. These things actually usually on the internet, they're not represented as strings, they're represented as binary numbers. But in machine or assembly language implementation, tries are even easier. You could just take a bunch of bits and use them as index into a table to move down the trie. And actually, tries are pretty old because it was so easy to implement data structures in that way in the past. You'd be surprised at how much of our computational infrastructure is built by programs or consists of programs that are written in machine or assembly language that can make really efficient use of low-level representations like this. But it's also useful in high-level languages. So what does it look like in an R-way trie? Well, all we're going to do is just do a search, and then we're going to keep track of the longest key that we encountered. So we have a path, and on that path, there's the most recently seen value. That's the longest key that we found. If we end at a null link, that's fine. If there's a value on that node that's got the null link, that's the value we're going to return. So that's a very straightforward implementation, just keeping track of the longest key encountered on the search for our key. That's the implementation of longest prefix of in the usual setup of making a recursive call, and this code is quite straightforward. Application of this one is so-called T9 texting. Now, when we do a course like this, we try to keep up with modern technology, and modern technology is moving almost as fast as we can. There are lots of young people who really don't know about texting with keypads anymore, but there's a certain range of 5 or 10 years where people got extremely adept at doing so-called multi-tap input, where the only keys on the phone were the 9 keys to dial numbers, and then we had 3 letters associated with each number, like on old dial telephones, and to enter a letter, you had to, like to enter an H, you had to tap twice, because that's the second letter on the 4 key. You had to tap 4 twice, and like that. The so-called T9 text input would use the kinds of algorithms that we're talking about to make it so that maybe you didn't have to do multi-tap. So rather than type 2 4s, it would do a try type search to figure out which word that you typed. And that looked good to us as a potential application for a while. I'm glad we didn't spend too much time on it. If you study this keyboard, maybe you'll see why. Well, you think about how to implement it. But once we get into it, we realized, Kevin realized, there's no S on this sample keypad. What happened to the S? What are we going to implement because there's no S there? So what exactly are they doing? This is maybe a bit of a fantasy that this is the response that he got. Maybe these people lived in a world with no S's. Anyway, we've moved on from tries, from that type of way of entering text. But I still want to mention just a few more ideas because the basis behind tries and ternary search trees is still out there and is still really an important part of our infrastructure. And there's some really great algorithms that we just don't have time to cover. One of them is an old algorithm called Patricia, and this one is a really interesting and intricate algorithm, particularly when implemented for binary tries where you just do a bit at a time. And people, again, implemented this kind of algorithm in machine language and got extremely efficient performance. If we cast it in the R-way tries that we've talked about, it's really the best way to think about it is a way to remove one-way branching. Seems wasteful to have all these nodes that just have one branch. And so one of the main ideas behind Patricia, there's others that don't really show up in the high-level representation we're using. But one of the main ideas behind Patricia was rather than associate a character with each node, associate a sequence of characters with each node. So you just don't have any one-way branching. Implementing this, it's maybe one step beyond this course, but maybe it's within what we could do in this course. We're just not going to take the time to do so. And you'll find implementations that in practice avoid the one-way branching that are used in many applications, performance-critical applications for searching nowadays. I already mentioned IP routing tables. There's probably no piece of code that's executed more often than that one, and that's based on a try-type algorithm. And we have these other applications listed as well. It's got some other names too. Another thing is a so-called suffix tree. So that's building a tree from a suffix table. We talked about having, for suffix sorting, we talked about applications. You can also build a search structure from suffixes of a string. That admits all kinds of fast string processing applications. And again, usually eliminate one-way branching in suffix trees. And also, amazingly, you can get them constructed in linear time. And there's all kinds of interesting applications of suffix trees. Probably the most important nowadays are in computational biology databases. Again, extensions of the kinds of algorithms that we've talked about today. So I think the bottom line for considering string search trees is that it's a real success story in algorithm design and analysis. It's a number of clever algorithms that really have made a difference in the kinds of operations that we can perform, in the amount of data that we can handle in modern applications. We started with red-black BSTs, which is a pretty good solution for general symbol tables, and also hash tables, which are also widely used. But with tries and ternary search tries, we have a performance guarantee where we only have to really access log n characters. And when you think about that, that's even when n is huge, that's going to be a pretty small number. So say we're looking among billions so billions of things, log n, even if you only have two-way branching, would be 30. And when we have 256-way branching, it's way smaller. And that's just the number of, so it's the number of characters accessed. And really the bottom line is, if you can set things up nowadays, even on the internet, when there's huge amounts of data out there, you can set things up so that you can only need to look at maybe 100 bits to get at anything. When you think about 100 bits, that specifies 2 to the 100th of possibilities. 2 to the 100th is a huge number. There are not 2 to the 100th pieces of information, even on the internet, even will ever exist on the internet in the life of this galaxy. But with just 100 bits, which really isn't too much, we can search for anything efficiently. That's an amazing success story for algorithm design and analysis. So that completes our look at tries and ternary search tries.